Collisions often can happen two-dimensionally, so we're going to look at a situation where we have a two-dimensional collision. So we have two cars, and they are, one is traveling east, a 900 kilogram car going east, and a separate one going north. This one's going 15 meters per second. The other one is going 20 meters per second, has a massive 750 kilograms, velocity of 20 meters per second. Okay, and they're going to collide and stick together. Okay, and then it says with velocity does the wreckage move just after the collision. Okay, so the goal here, velocity meaning both magnitude of velocity and direction. Okay, so we want to find these two things. Okay, well, we can imagine they're gonna collide and move off together in that direction. Okay, and so when we do this, we're gonna have to analyze the x direction and the y direction separately. Okay, and as we do this, what I'm going to do is I'm going to analyze the x direction, and I'm going to have you analyze the y direction, and so we can get both vx and vy afterwards. So the key here is that the cars are going to stick together, so that means they're going to travel with the same velocity after. And so I'll go ahead and set up for x. So we're going to go we'll call this car A and this car B. So the momentum of A before plus the momentum of B before is going to be equal to the momentum combined of A plus B together afterwards. Okay, and if this is looking at the x direction, then car B has zero momentum because it's traveling directly north. And so we can say, okay, you have nothing. You have no momentum that way. Okay, and so we could say, all right, so momentum is m times v, so 900 kilograms times 15 meters per second will be equal to whatever their momentum is afterwards. Okay, so their combined mass, which is 900 plus 750 times the Vx, or the velocity in the x direction. We could also say V cosine theta if we want, but we'll just use Vx for now. Okay, and so from here we can solve for Vx, and we get that Vx is equal to, and so I get that Vx, velocity in the x direction, is about 8.2 meters per second. Okay, so now I would like for you to do this same process, but in the y direction. And so as you do, instead of solving for Vx, you're solving for Vy, and you know that there's no velocity from this car in the y direction initially, so the momentum from car A this time for y would be equal to 0. Go ahead and solve for that. Once you do, we're going to say momentum A plus momentum B will be equal to momentum of A plus B. As we said, this will be equal to 0. Okay, so we finished solving, substitute values in, combined mass, 750 times 20, we get a velocity of 9.09 for the y direction. So that means that afterwards they have an upward velocity, or to the north, of 9.09 meters per second, a velocity to the side of 8.2 meters per second, and so that would be a magnitude equal to the square root of 8.2 squared plus 9.09 squared, and so we get about 12.2 meters per second as the velocity. Okay, and then for the angle, this angle, we can say tangent of that angle is equal to 9.09 over 8.2. Do inverse tangent to solve it, and we'll get here 47.9 degrees north of east. So we get velocity and direction, or magnitude of velocity and direction for our collision here. Okay, so two-dimensional momentum collisions. We'll do some practice with these. I didn't feel the need to walk you through another example. It's just like one dimension, except we have to do it twice. once for y, and once for x. Okay? There could be a scenario where they don't collide, or where they collide but they don't stick together, so they have separate velocities. But in all those cases, we would know the velocity of one of them afterwards, so we could solve for the other. Okay? And that's going to wrap up this video, so please let me know if you have any questions.